What is principal component analysis (PCA) and why is it used in machine learning? PCA is a dimensionality reduction technique used in machine learning to simplify datasets while retaining as much information as possible. It transforms data into a set of new variables called principal components which capture the maximum variance in the data. PCA is useful for reducing computational costs, removing noise, and helping visualize high dimensional data. What are the key steps involved in performing PCA? Spacet can. The main steps in PCA include standardizing the data equal importance of features, calculating the covariance tricks to measure relationships between features, computing eigenvalues and eigenvectors from the covariance matrix, sorting eigenvalues to determine the most important components, transforming the original data onto the new principal component axis. How does PCA achieve dimensionality reduction? PCA reduces dimensions by selecting the top principal components which capture the most variance in the data. These components represent a combination of original features, hugging faces that allowing the dataset to be represented with fewer variables while retaining significant information. And what are eigenvalues and eigenvectors and how are they used in PCA? Eigenvalues measure the importance when variance captured by each principal component, while eigenvectors define the directions of these components in the data space. In PCA, eigenvectors identify the new axis and eigenvalues help prioritize them. What is the role of the covariance matrix in PCA? The covariance matrix represents the relationships between features in the data. PCA uses this matrix to identify patterns of variance and compute eigenvalues and eigenvectors, which are central to finding the principal components. Can PCA be applied to non-numeric data? Why or why not? PCA cannot be directly applied to non-numeric data because it relies on mathematical operations like calculating variance and eigenvalues, which require numerical inputs. Non-numeric data must first be converted into a numeric format, such as using encoding techniques. What does it mean for a principal component to explain variance in data? A principal component explains variance by showing how much of the data's information variability it captures. Components with higher explained variance contribute more to understanding the structure of the data. What are some practical scenarios where PCA is beneficial? PCA is useful in tasks like image compression, noise reduction, gene expression analysis, and visualizing high dimensional datasets. It is also widely used for speeding up machine learning models by reducing feature dimensions. Now, how do you decide the number of principal components to retain? The number of components is typically chosen based on the cumulative explained variance, aiming to retain enough components to capture a significant percentage G, 95% of the total variance. Slots and eigenvalue thresholds can also guide this decision. How does scaling or normalization affect the outcome of PCA? Why is it important? Scaling ensures all features have equal weight in PCA. Without scaling, features with larger ranges dominate the variance, leading to biased principal components. Normalization helps create meaningful components by standardizing the data. What are the limitations of PCA, particularly with nonlinear data? PCA assumes linear relationships between features and cannot effectively capture complex, nonlinear patterns. Additionally, PCA may lose interpretability of features and struggles with datasets where variance does not align with important data characteristics. Can PCA be used for feature selection? Why or why not? PCA is not typically used for feature selection because it transforms data into new variables, principal components, rather than selecting original features. However, Hugging faces that it can indirectly guide feature importance by showing which features contribute to significant components. What are the computational challenges of PCA with very large data sets, and how can they be addressed? For large datasets, calculating eigenvalues and eigenvectors can be computationally expensive. Techniques like randomized PCA, incremental PCA, or using specialized tools such as singular value decomposition (SVD) can help address these challenges. How would you evaluate the success of dimensionality reduction using PCA? Success can be evaluated by checking how much variance is retained by the selected components, assessing model performance improvements, or visualizing reduced data to ensure meaningful patterns are preserved. In what scenarios would you not recommend using PCA? PCA may not be suitable when data relationships are non-linear, when interpretability of features is crucial, or when feature scaling is problematic. It is also less effective when most of the variance is irrelevant noise. How does spaces that PCA interact with supervised learning algorithms like logistic regression or SVMs? PCA is often used as a preprocessing step for logistic regression or SVMs to reduce dimensions, speed up training, and improve model performance. However, it may lead to information loss, which can slightly reduce predictive accuracy. If the first two components explain only 50% of the variance, what steps would you take? If only 50% of the variance is explained, you could retain additional components to capture more variance. Reassess if PCA is the right tool for the dataset. Explore alternative dimensionality reduction techniques like TSNE or UPM. How would you compare the effectiveness of PCA versus dropping features manually based on domain knowledge? PCA is data-driven, using variance to determine components, whereas manual feature selection relies on domain expertise. Combining both approaches can sometimes yield better results, as PCA might miss features with low variance but high relevance.